Okay, we're going to continue on here and talk about gases is what we've been talking about. So last time we talked about a number of gas laws. I think we had our Charles law, our Boyle's law, I'm sorry. Our Charles law here, V1 over T1 is equal to V2 over T2. Our Guy-Lussac's law, P1 over T1 is equal to P2 over T2. We had our Avogadro's law, which is V1 over N1 is equal to V2 over N2. And putting those guys together gives us our ideal gas law, which is our PV is equal to nRT. And remember, on some of these relationships here, when we talk about Boyle's law, as the pressure goes up, the volume goes down. And as the pressure goes down, volume goes up. When we talk about Charles' law, as the volume goes up, so does the temperature. As the volume goes down, so does the temperature. Here, in Guy-Lussac's law, same sort of pattern. Pressure goes up, so does the temperature. And pressure goes down, so does the temperature in that case. In terms of Avogadro's law, we had a relationship that basically the number of moles is equal to the volume when we're at constant pressure and temperature. So at constant pressure and temperature, we have our volume and moles being basically equivalent to each other. Our ideal gas law is the most restrictive in terms of units. Pressure is an atmosphere. Volume is a liter. N should be moles. Temperature does need to be in Kelvin. And that goes pretty much for all gas laws. Whenever there's temperature involved, it does need to be in Kelvin. Again, as we talked about, even if they sort of give you the value in Celsius and then want the answer in Celsius, you do need to convert it to Kelvin to go into the gas law and then convert it out of Kelvin for the answer. All that's based off of R, which is 0.08206 liters, atmosphere, Kelvin, and mole. And we talked about STP, which is standard temperature and pressure. And that does represent a values. Temperature is 273 Kelvin. Pressure is 1 atmosphere. And when you are at STP, there's a relationship that at STP, 1 mole of any gas will equal 22.414 liters. So this is a conversion that you could use when you're at STP, and it will allow you not to have to use the ideal gas law, for example. You can kind of bypass it. You can use the ideal gas law for any conditions, be it STP conditions, non-STP conditions. You could always go into the ideal gas law. So as we might have talked about last time, if you don't want to worry about using this in a wrong situation, you could just forget about it and just use the ideal gas law in every situation that it applies to. We, I think, finished with the combined gas law, if I'm not mistaken. And the combined gas law is P1 V1 over T1 equals P2 V2 over T2. Once again here, temperature does need to be in Kelvin. Temperatures can be any unit as long as, not really temperature needs to be in Kelvin. Pressure and volume can be any units as long as they are the same on both sides. As I mentioned before, this is a really good gas law to know, or even the version where you still have the moles in there, which looks like this. That's because you pretty much can get all the other gas laws that are up here from that gas law. You basically just scratch out what is not given to you, what's being held constant in that particular problem. So again, if there's no mention of moles or temperature, you just scratch it out and you have Boyle's law given to you. If there's no mention of like pressure and moles, you could just scratch out pressure and moles on both sides. And now you have Charles' law given to you. So If you remember, again, the combined gas law and the ideal gas law, you pretty much will have at your fingertips of all the gas laws that you would need. You could just, again, scratch out what's either being held constant, what's not mentioned in the problem, and you'll be finding the right gas law to probably use. Any question on any of those things we talked about last time there? All right, so I believe we did this one, correct? Yes. So then let us talk about a couple of calculations that might be a little bit new for you in terms of gases, and that is calculating the density of a gas and also calculating the molar mass of a gas. As we talked about earlier, when we calculate the density of gases, typically the units that we end up with are grams per liter as opposed to grams per milliliter, which is typically what we see with liquids and solids. Density is mass over volume, and to solve for it, this is the pressure in atmospheres. That is our gas constant. That's our temperature in Kelvin. And that is our molar mass in grams per mole, basically. To calculate the molar mass of a gas, which means that you're going to end up with units of grams per mole, you could take the density in grams per liter times the gas constant and our temperature and our pressure in atmosphere. The reason why our pressure, for example, and our temperature and all those things kind of need to be in the same units as the ideal gas law is because both of these equations are pretty much based off the ideal gas law. So the good news is you don't even really have to remember these equations. You could really get to them through the ideal gas law and just thinking about units, which is kind of a good thing. Or you could obviously remember these formulas and plug and chug into them. But really, they're both based off of using the ideal gas law to get to the end. So let's take a look at a couple of examples here. So once you try this one here, we have 2.1 liter vessel contains 4.5 grams of a gas at 1 atmosphere and 27 degrees Celsius. What is the molar mass of the gas in grams per mole? So why don't you take a moment and see. Okay, so let's take a look. So like I said before, you can, if you wanted to, just plug and chug, obviously, it's an equation that we have on the previous page. But again, just in case maybe you can't remember it or not sure, you could really still use, as I mentioned, the ideal gas law. So let's see how we can maybe just use it that way in case you can't remember. So first off, we're looking for the molar mass, which is grams per mole. So when we actually sort of pull out the information from the problem, we see that it contains 4.65 grams of a gas. That is the top part. So we actually have the top part already given to us, which is the grams. What we need to get to the molar mass is the moles, and that again is where really the ideal gas law is going to come into play. If we take our PV is equal to nRT, in this case, we have a volume that is 2.1 liters. So we have a volume. We have pressure that is in 1 atmosphere. So we have pressure. And we have temperature that is 27 degrees Celsius, which means we do need to convert it into Kelvin there. So we're going to add 273 to our 27, going to give us 300 Kelvin. And we always have R, that's a constant given to us, or we have available sort of to us here. So that is where the moles part is going to come really from the ideal gas law here. So we're going to solve for N. N would be, we're going to divide these guys to the other side. That will give us PV divided by RT. And if we do that, putting in our numbers, and this is why we really do need to make sure sort of our gas values are in the proper units for the ideal gas law, because even again, that formula on the previous page is based off the ideal gas law. So we want everything to cancel out correctly. We'll take our R. And our temperature of 300 Kelvin. Again, everything's going to cancel out here except for moles. And that will get us 1 times 2.1, 0.08206 times 300. 1 2.1 divided by 0.08206. Try maybe the divide button would be better. 300. There you go. Gonna give us 0.0853 moles. And that's gonna be really the bottom part that we need. So our molar mass in this case would be our 4.65 grams divided by our moles here. And that's going to get us 4.65 divided by our answer. About 54.51 here, or 54.1. 54.5 grams per mole as our molar mass. Yeah, so you use this equation, right? Basically, yeah. Yeah, so that's what I said before. You can use this equation. This equation is really based off of the ideal gas law. But I was showing it the other way, just in case you couldn't remember this equation. You could kind of go back to the ideal gas law. But this one's basically based off of that. And that's why there's the P, R, and T, which comes from really the ideal gas law. The density is where the volume is hiding, basically, from the ideal gas law in there. So that's essentially where it comes from. So yeah, like I said before, you can definitely plug and chug into this equation. But if you should happen to maybe forget that equation, not sure about it, you could still just sort of solve it, kind of following the units and using the ideal gas law. And you can use it that way for either of those equations we saw on the previous page. Top one is also based really on the ideal gas law. So both work, both are fine. As you can see, they both should give you the same answer. Other questions? All right, let's try another one here. What is the density in grams per liter of oxygen gas at 778 torr and 27.5 degrees Celsius here? Okay, so let's take a look. So once again here, you absolutely, if you know their equation, you could plug it into that equation and you should get the right answer. But once again, if you maybe don't remember that equation or something's going on, we could still think about the ideal gas law and it could sort of help us kind of get us there. In this case, we have a pressure that is 778 torr, which means we do have a pressure. We do have a temperature that is 27.5 degrees Celsius, and we always have R available to us. We do need to do some conversions on these guys, especially if we're going to use the ideal gas law, or if you're going to use that previous equation as well, because it's really based off of the ideal gas law. So we do need to divide our torr here by 760 to convert it into atmospheres. And that'll give us 1.02 atmospheres. We need to add a 273 to our temperature there. Gonna give us 300.5 Kelvin. So what can I do with this ideal gas law? I could actually solve for N divided by V. So if I take my V this way, and I take both of these guys that way, that will give me P over RT in this case. And N is moles, right? And V is liters, and that is moles per liter. That's really the molarity of our gas if we solve for N over V using the ideal gas law. And that's good because at that point, it is a conversion factor to get to grams per liter. And that would be the molar mass that allows us to do that. And that is how that other equation comes about, is derived again from the ideal gas law. So once again, you can kind of fall back on this if you need to. So if we do that, we will solve for N over V, which will give us the molarity. And that will give us 1.02 atmospheres divided by our gas constant. And our temperature of 300.5 Kelvin. And that will get us here, 1.02 divided by 0.08206 divided by 300.5 can give us 0.04136. And this would be moles per liter, as the atmospheres will cancel, the Kelvin will cancel, And when you divide the bottom number, the units flip up to the right way that you need. This is where we're going to use our molar mass, but we also need to remember that it is O2 and not just oxygen. So we do need 32 grams per mole as our molar mass for O2. The moles will cancel, and now we will be left with the units that we need, which are grams per liter. So we'll times that by a 32. Going to give us a density of 1.32 grams per liter in this case. So as you can see, pretty much that other equation is also really based off of the ideal gas law. Pretty much all of them are. So you could really always sort of fall back to that if you're at a loss for maybe how to go about it. And you can just think of it as more of a unit sort of conversion type problem and just kind of get yourself to the right units that you need. Question on density or molar mass calculations. All right, then the next thing we're going to talk about is gas stoichiometry. And the good news about gas stoichiometry is still stoichiometry. So it's pretty much the same steps. If you have a basic gas stoichiometry problem, it's the same 4 steps as a basic stoichiometry problem, which again are pretty much what we see up here. We need a balanced equation. We need to convert to moles. We need to do a mole to mole relationship and convert those moles to some other unit. The main difference in a gas stoichiometry problem is most likely somewhere along the way, you're going to probably find yourself using the ideal gas law. And the 2 common places in a basic stoichiometry problem that involves gases that you would do that is you could do it up front here. And instead of using grams in the molar mass to get to moles, you could actually solve for moles from the ideal gas law and just kind of continue on with a normal sort of stoichiometry problem at that point. Probably in a lot of cases where you most likely will use it is at the end of the stoichiometry problem. And in a lot of cases, you're solving for the volume of gas that you would be making. So you, at the end, you would sort of put it into the ideal gas law and solve for volume. And that's a very common place. So those are 2 of the most sort of common places that you will sort of insert the ideal gas law. Really, everything in between is sort of the same. The only other thing that you do need to watch out for in a gas stoichiometry problem, solution stoichiometry problem, doesn't really matter what type of stoichiometry problem is it a limiting reagent problem or not? So you always got to kind of keep that in the back of your head. A reminder that the way you can determine if it is a limiting reagent problem is you have enough information, whatever information is given to you, to get to the moles of the reactants, both reactants. So if you have a way from the information given to you in the problem that you can simply get to the moles of each of those reactants, either through grams in the molar mass, using the ideal gas law, molarity and volume, whatever it may be, then it is a limiting reagent problem. And you do need to do, obviously, the limiting reagent sort of calculation. If it is not that type of problem and you don't really have enough information to get the moles of both reactants, then you just roll with a basic stoichiometry problem. And again, at some point, you'll use that ideal gas law. Any questions on that there? So if we look at this here, we want to know what volume of CO2 would be produced at 37 degrees when we have a pressure of 1 atmosphere and 5 grams of glucose are used up. So in terms of glucose here, we got 5.6 grams of it. And for our CO2, which is our gas, we're looking for the volume. We have the temperature is 37 degrees Celsius. We have the pressure is 1 atmosphere. So in this particular case, if we think about the ideal gas law, PV equals nRT for the CO2, we have a pressure, we have a temperature, we always have R, and we are looking for volume. So the one sort of thing that is missing for us to sort of get to volume is the moles of the CO2. So if we think about really the only piece of information that's left at this point is just the 5.6 grams of our glucose. So this tells us 2 things. we're going to use the stoichiometry really to get to the moles of CO2 so that we could use the ideal gas law at the end of the calculation. Secondly, when I look at this, I could clearly see there's nothing mentioned about O2, which means there's no way for me to get the moles of O2, which means this is a basic stoichiometry problem, right? It's not a limiting reagent problem or anything like that. So because of that, we'll roll into our 4 steps. We have the balanced equation given to us. We need to then convert to moles. So we do need the molar mass of this guy. So that's going to be 6 times our 1201 for our carbons, plus 12 times our 1.008 for our hydrogens, and 6 times our 16 for our oxygens in this case. And that's going to get us a lot, I'm imagining. Looks like 180.2 grams per mole. So our second step here is going to be like a traditional sort of stoichiometry problem. We're going to take the 5.6 grams of our glucose. We're going to use the molar mass from the periodic table to convert that into moles. The grams will cancel here, and that will get us, if we get an answer at this point, about 0.03108, we'll call it, moles of our glucose. Once again, here we're not interested in glucose. We want to go from glucose to our CO2. So from the equation, we can see 1 mole of our glucose will equal 6 moles of our CO2. So this is the stoichiometry part and really the third step here. So at this point, it's still just a basic stoichiometry problem. We're going to use our third step, 0.03108 moles of glucose. From the equation, again, 1 mole of our glucose gives us 6 moles of our CO2. So that will give us times 6. And that looks like we end up with 0.1865 moles of CO2. And because of that, we now have the moles of CO2 that we need for our ideal gas law. So what's left is to obviously solve for volume here. Our pressure is in the correct unit, but like most gas ones here, we do need to convert our temperature into Kelvin. So that's going to be a 37 and a 273, 310 Kelvin. And at that point, we can solve for volume. So volume will be nRT divided by P in this case. And putting in our numbers, our volume will equal our moles, 0.1865. Our gas constant, our temperature, which has been converted to Kelvin, and that's all going to be divided by our pressure, which in this case is actually just 1 atmosphere here. So popping that in, 0.1865 times 0.08206 times a 310, going to get us, I'll go up here on top, a volume of 4.74 liters of CO2 would be produced. That would be, by the way, a theoretical yield, as that's a product. So in this case, that would be the theoretical yield of the volume of CO2 that you would produce. Any questions on that? So this particular one here was really a basic stoichiometry problem up until the 4th step. So instead of using the molar mass on the last step here, we went into the ideal gas law and solved for volume, which again is a very common sort of way that you will solve some of these problems. Any questions on any of those steps there? All right, I did one. Once you do one here and see, let's do this one, which we're going to do coming up in one of the experiments. I think 12, we're going to do this one. Calculate the volume of hydrogen gas that you would produce at STP if you started with 5 grams of magnesium and excess amount of HCl. Magnesium like 20. Okay, let's take a look at this since we're getting to the end. In this case, obviously, we are dealing with stoichiometry. We do have STP. Remember that when you are given STP, it does represent two values. The temperature is 273 Kelvin, and the pressure here is 1 atmosphere. So we do have those two things. That means, again, if we sort of think about our ideal gas law, which we might want to use, we do have temperature, we do have pressure. Here we're looking for the volume again. We do have R. So we are going to, if you choose the ideal gas law here, we're going to need to figure out the moles of our hydrogen gas. The only other piece of information we're really given is that we're starting with 5 grams of magnesium. So once again here, we don't have anything mentioned about HCl. So it's definitely not a limiting reagent problem. So just a basic stoichiometry problem here. We have our balanced equation. We're going to convert into moles. So we'll take our 5 grams of magnesium. We're going to use the molar mass from the periodic table, 2431 grams per mole. And that's going to get us there, 5 divided by 2431. We'll go with 0.206 moles of magnesium. Here we're going to use the mole-to-mole relationship between magnesium and hydrogen because that's the gas we're looking for. In this case, it's a 1-to-1 relationship, which makes the stoichiometry pretty straightforward. 1 mole magnesium gives us 1 mole of hydrogen, which means we end up with 0.206 moles of hydrogen. At that point, we now really, if we go with the ideal gas law here, have everything that we need for the ideal gas law. We could solve for volume, which would be nRT divided by P. Put it in our moles, 0.206 moles, our gas constant. Our temperature, which is 273, all divided by our pressure, which is 1 atmosphere in this case. And that's going to get us there. Hit the right buttons, it'll get us there. 4.61 liters of H2, which would also be a theoretical yield in this particular case. Any questions on that calculation there? Could I have solved this a different way? I could have in this case because we were at STP. So this is a situation where you could have used that conversion that we saw that at STP, 1 mole of any gas will be 22.414 liters, which means you really could have kind of picked it up right about there. And once you got that number, you could have just used that conversion factor of 22.414 liters is 1 mole. Moles will cancel and it will get you there as well. So as you can see, this would be the appropriate price if you wanted to use that conversion factor because we were at STP. Once again, you cannot use it if you're not at STP, but you can always use ideal gas law as you see above there. So you use ideal gas law in any conditions. So like I mentioned before, if you're not sure you should use it or maybe you feel like you might use it wrong, you could still put everything into that ideal gas law and use it for STP conditions, non-STP conditions. It doesn't really matter. Yeah. Any questions on gas stoichiometry? So really, again, just the basic steps, other than somewhere along the way, you're going to use that ideal gas law. Maybe